Hello, this is Bob Cox again. Welcome to the sixth talk in the series about fMRI task-based data analysis and individual subject regression models. Now I'm going to turn to more advanced regression models that can be used in AFNI, and that will include a collection of things, some of which are related to others, and others are just random things that you should know about. Regression models in AFNI are usually set up using the AFNI proc.py superscript. This script in turn uses a bunch of different programs to carry out its objects. The one that uses to create the regression matrix is called 3D Deconvolve. 3D Deconvolve can also be used to solve the linear system, or another program called 3D RemoFit, which I'll discuss in the successive talk after this one, or 3D T-Project, which is used for resting state regression. I'll discuss that one at the end of this talk. This set of slides covers more complicated model setups which are used for special cases, but really, isn't your research special? One weird little thing that is allowed is all zero time series regressors, a column that's all zeros. That is to say, there are no stimulus times for a regressor in that class. And it requires a special option to do that because otherwise that would be an error. Mathematically, it's like asking the question, x times 0 equals 3. What is x? It doesn't have an answer. So what would the logical answer be? We'll just give that beta weight for that regressor 0, and we'll give it a 0t statistic. Why would you want to do this? Well, suppose you're carrying out an experiment on a bunch of subjects, and the task is a subject has to make a forced choice for some visual stimulus. Say a face is projected, and they have to decide is it a male or female face, and they press a button. So then you want to analyze those correct trials and incorrect trials as separate cases. You may not even be interested in the incorrect trials, but nevertheless, something different happened in the person's brain when they were making an incorrect trial. So you need to separate out those trials into a separate class and put in those times into a different file than you would for the correct stimulus class. And then what happens if you have a subject that makes no mistakes? Well, if you need mistakes, then you need to make a harder test. But if you're really interested only in the correct ones, then you can do this where you keep the all zero regressor, where you put in the stimulus time file just contains a star, indicating that it's a placeholder. It's not a non-existent file, but the star means don't do anything. Then the input files and the output data sets for the error making and perfect subjects will be organized the same way. There'll be a regressor, and there'll be a beta for the correct trials. There'll be a t statistic for the correct trials. There will be a beta for the incorrect, and a beta for and a t statistic for the incorrect. And this makes it a lot easier to set up group analyses when all your subjects have inconsistent output files from the single subject analysis level. Other basis functions can be used for models. 3D Deconvolve has a dozen or so different possibilities, most of which are very specialized. Block and tent have been covered in previous talks in this series. One I mentioned briefly is C-spline or cubic spline, which instead of tent, which is technically a linear spline. The cubic spline is made up of pieces of it are made up of cubic polynomials, and it's basically a drop-in replacement for tent, and it gives a smoother response shape in which you can get out of the program, and it'll show you the response shape. And here's an example of real data that was regressed with C-spline, given the red curve, black curve, you use tent, and you can see they give pretty much the same shape, but one looks more plausible than the other, simply because it doesn't have corners in it. So there are sort of two different types of basis functions available. One where there's a single beta for the basis function, and those that have multiple betas. The single beta functions, the beta is basically the amplitude. It is the amplitude. It's the size of the shape that was needed to fit the data the best. The block we've discussed a lot. The GAM was discussed briefly. It's for short responses. The block is basically the GAM stretched out over time. There's another one called 2GAM, which is the sum of two different GAM functions, usually one with a negative component. This is for compatibility with the Brain Voyager software. The SPM-G1 we discussed briefly before. It's a special case of the 2GAM and is provided for compatibility with the SPM software. Just for completeness, I'll mention the wave function. This is a very old AFNI waveform, which goes back to 1994, I think. Don't use this one. Myon is for use with experiments where you've given Myon contrast agent. This is an agent that provides a huge signal change, much bigger than the 1% of bold, maybe 50% signal change. It's only used in animals, though, because it's mildly toxic, and it's not a good plan to poison your subjects. Block and Myon always take a duration parameter, saying what is the duration of the stimulus. And the GAM, the 2GAM, the SPM-G functions, and wave have optional duration parameters. Otherwise, they're built for brief responses. Then there are the basis functions that return multiple betas. The tent and its friends, C-splin, tent0, and C-splin 0 have been previously discussed. SPM-G2 and SPM-G3 were also previously discussed. Unlike all the other multiple beta functions, they can also take an optional duration parameter. All the other beta functions just use a duration over which the basis functions are defined. And the other ones that are there are very special advanced users. Poly, which gives you the Legendre polynomial expansion in time across whatever unit of duration you wish. A sine, which gives you the sine series expansion. And EXPR, which gives an arbitrary set of formulas. That is for someone who really knows what they're doing. Here's the examples of some basis functions that have single betas. From the bottom to the top, we have the block. This is for a stimulus that starts at 10 seconds in, 10 TRs in, and has a duration of 20 TRs. And this is the block at the bottom. We have the GAM with a duration at the same duration just above it in red. Above that is SPM-G1. Above that is Myon, and above that is one from the EXPR that I threw in just for fun with the sine squared. Now, the difference between the block and the GAM is so small that it could have no practical difference whatsoever under any circumstances. SPM-G1 is a little bit different because it has this undershoot which drags down the end of the block as well. And that is probably still a very little practical difference because, remember, it's least squares fitting, so fluctuations that are 5 times smaller count 25 times less than the main body of the fluctuation. The Myon shape is considerably different because it's a pharmacological agent that takes time to have an effect up and down. And the sine squared is just for fun, as I said, and it looks cool. And the script for producing these is given, these plots are given here, and you can download these from the AFNI website. Now I'm going to switch to something a little different, and that's what I call individual modulation regression. The idea here is to compute a separate amplitude of response, a separate beta for each stimulus block in each stimulus class. If I show 20 faces to the subject, instead of getting one beta for the average face response, I'm going to get 20 betas, one for each time I show the face. That, of course, requires a separate regression column for each stimulus time. So instead of having one regressor for faces, now I'd have 20. Now, the betas for each of these separate blocks or events will be a very noisy thing. You can't use these individual activation maps for much because, I mean, imagine you have a 10-second stimulus and a TR of 2 seconds. Then basically 5 or 6 time points go into the calculating the beta. And considering the amount of noise in the fMRI data, the individual betas are going to be shot full of noise. So you have to pool these in some further statistical analysis. If you're doing voxel-wise analysis, you could do this with t-tests in 3D t-test++. You could do intervoxel correlations in the betas. You could correlate the betas with something else. You could also use these for um, pattern analysis in the brain, things like that. This is where you have to have imagination. Really, we haven't used the IM much, with an exception I'll mention in a moment. The first application of it was just checking some data received from another institution. In this experiment, there were 64 blocks of sensory motor tasks, 8 runs, and each had 8 blocks. And it was a very strong analysis. And then there were 4 runs on the first day and 4 runs with the same subject on the next day. And in most of the subjects I analyzed from this other institution, the results were very clear. In this one subject, the results were much weaker, and I couldn't understand why. And so then I used the IM program, which I had just developed a few weeks earlier, to calculate the 64 block betas. So what you're looking at on the right is a graph of not the data time series, but the beta time series. So we have betas from each of the 64 blocks across, and the vertical grid lines are set to run every 8 points, so that means that each grid line demarks an imaging run. And you can see quite clearly that on the fifth block of blocks, which is to say the first run of the second day, a whole bunch of negative betas. And if you analyze it the normal way with a single regressor instead of 64 regressors like this, then you get kind of the average of all these things, and then the negative ones tend to cancel things out, and you get weaker results for this subject than you would. And I sent an email to the people at the other institution, and after a little bit of hemming and hawing, they agreed that they had some sort of sign error in the stimulus for that imaging run, and I think they had to withdraw that data. So IM naturally works with blocks which only have one amplitude parameter beta for a given stimulus start time. It's more difficult to imagine using this with multiple beta basis functions like splines, because then each event gets not just a different amplitude but a different shape, and now you have so many regressors. The word overfitting should leap into your mind. Just difficult to imagine how this would work in practice. I want to mention some work that's now in progress, that to use the multiple betas that result from IM regression and then combine those in a linear mixed effect model. So to calculate where the noise is not just the fluctuations that come from the measurement, which is estimated, that noise is estimated from the residuals, but the randomness from the subject response fluctuations. That is, so we calculate the randomness from the noise and the randomness from the fluctuations in the subject response, and that's 2 kinds of randomness mixed together, which requires using what's called a linear mixed effects model. And the promise of this is that it can give more robust results than just assuming that there's a mean subject level response and there's no variability in the subject level response. Here are the kind of regressors you get for an IM analysis. If we have blocks, we have 10 different stimuli in different block start times, but instead of being one regressor with a lot of waves, we have 10 regressors, each with 1 wave. On the left is the graph of the regressors, and on the right is the image of the regressors where time runs down, whereas on the graph on the left, time runs left to right. And those plots were produced with this script, which you can also download. Immediately after the IM regression, I developed the AM regression, which is generally more useful, which is why I have more slides for this. AM is what I call it, amplitude modulated regression. Other software packages, I believe, call it parametric modulated, but it's just a name. The idea is that you have some extra data measured about the response to each individual stimulus. So you have 20 faces and you have some extra information, and you think maybe your whole experiment is designed that the bulge response is modulated by this extra information. And you can imagine the extra information would be reaction time. You know when you presented the face, and you know when they press the button saying something about the face. or maybe galvanic skin response, or whatever that's called these days, or pain level perception. And you want to see if there's some brain regions that vary, where this bold response varies proportionally to this ABI, I call it here, a personal acronym for auxiliary behavioral information. Mostly used in these slides because that way I don't have to write auxiliary behavioral information 1,000 times. Well, if you just have two levels of ABI, yes or no, then that's really just two different kinds of stimuli, the yes ones and the no ones. But if you have multiple levels, usually you think of those as continuous, then, well, our analysis is linear regression, so we have to assume that the change in the measured signal, the bold data, is proportional to the changes in the ABI values. If you have a bigger ABI value, then you get a bigger bold signal. That would be a positive effect. You could also get a smaller bold signal if you have a bigger ABI value. A negative slope is perfectly legitimate. If you really need to, you'll have to find some transformation for the ABI values, for example, a logarithm. Although I'll discuss briefly an approach which can be used for mild nonlinearities in the bold response, if you have enough data. You need to make two separate regressors because there are two statistical questions here. One regressor is to find the mean functional MRI response. That's the usual analysis. And the other one is to find the variations in the fMRI response as the ABI data varies. This second regressor, whose formula is given above, there have to be formulas. It's a computer program that does math. So that is the sum over all the time of the times for the stimuli, which are here symbolized by the Greek letter tau sub k. The hemodynamic response is set to for h of t is set to start at t equals tau sub k. So h of t minus tau sub k, t minus tau sub k is 0 when t equals tau sub k, and then h will go up and down following that. And then each one is modulated by its difference between the ABI value supplied minus the average ABI value. That's because this one is modeling just differences, the fluctuations based on the differences in the ABI. The one where we just cross out this AK minus A bar thing, this is just going to be the regular regressor. If you really want, you can set it so that the mean of the AK is not removed, but this is for if you know what you're doing. Say you wanted to remove the median or something like that. So the beta for the first regressor is just the standard activation map, what you'd get without even thinking or having heard of AM. The statistics in the beta for the second regressor give you an activation map of voxels whose bold response changes with the changes in ABI. And it's necessary to have two regressors to allow separation of voxels that are active but not modulated by the ABI from voxels which are ABI sensitive. And I'll give you a slightly graphical explanation of that in a moment. But remember, there are two questions, and a statistical analysis, when we say, is this beta equal to 0 or not, is one question. If we have to have two questions, we have to have two betas, which means two regressors. So the usage is in AFNI Park Pi, you say the Stim types is AM2 as opposed to just standard times. The timing file is a little bit different than the others because the ABI values get married to the time values. And in this cartoon example in the red box, we have on the first imaging run, we have 4 stimuli times 10, 23, 27, and 39 seconds. And then 5, 4, 2, and 5 are the values that are married to that, separated by the asterisk character. And 1 line per imaging run, as usual in AFNI. So the second imaging run, we have 2 stimuli in that class. The third imaging run, there are no stimuli in this class. Presumably there are some other classes of stimuli. That's placeholder then. The star just indicates don't do anything for that run. And then the fourth run has 4 more stimuli. So each stimulus is time star ABI. So you can create such a file from 2 standard ASCII text files using the program called 1D Marry, and it has an option to let you split them up. So the matrix creation program automatically creates both of these regressors, and then you can use the statistics to test them together or test them separately. If you want, the AM1 regression is also available, only building the regressor proportional to the ABI parameter itself. This was added mostly for checking things, but it turned out to be useful when the duration modulated analysis was added a year or two later, which will be described real soon. You can have multiple amplitudes married to the stimulus times. You can have multiple ABI, and I'm not going to make any polygamy jokes here. But and one application of this has been to fit a response model using cubic polynomials, that is to say, nonlinear in the ABI value A, by giving the three values in a polynomial expansion in A. For example, the simplest thing would be to supply A squared, and A cubed married to each time. But it's a little better to do that using Legendre polynomials. If you really need to, you can contact us to find out how to do that. The better solution would be to ask your local physicist, because I tell you, physicists just love Legendre polynomials. They do this in graduate school for years. So here's a toy example where I just made up some numbers, where we have a file at the top of the screen with 10 seconds, 30 seconds, 50 seconds, and so on, regular stimulus times, married to numbers 1, 2, 3, 1, 2, 3, and so on. And then here's a 3D Deconvolve command that produces just a naked matrix file. It doesn't have, no data is input, so therefore that it can't do any analysis without data, but it produces the matrix file, and with no polynomial baselines, because we don't want to plot those. And here then we just plot the matrix file, and you can see it's 1, 2, 3, 1, 2, 3, 2, 1, and so on. So it looks like what you might expect it to look like, which of course is good. This script can produce this plot and the plot on the next page, which you can download, of course, from our website. AM2 regression is done in the same way, except the AM1 on the previous slide is replaced with AM2, and we produce this output matrix. The matrix now has two columns, because that's what AM2 means, huh? And so then the first regressor, the bottom curve, is the standard regressor. Up, down, up, down. It doesn't care about the ABI. The second regressor is not like the regressor on the previous page. It's basically the difference between that regressor and this regressor, where the amplitude here is negative because the mean of all these 1, 2, 3s, 2, 1, 3s, and so on is about 1.8. So 1.8, the mean, we subtract 1.8 from 1, we get a negative number. Here's the amplitude. For the 2, 2 minus 1.8 is a small positive number. We get a little bump. 3 minus 1.8 is a big positive number, so we get a big positive bump, and so on. And so basically, then in the mathematical jargon, in the time series of the data here, which here has, I think, 200 time points, then we're searching in that 250 or whatever dimensional space of possible fluctuations. We're searching for those that fit in not this one-dimensional space that looks like this, but in a two-dimensional space that looks like this times some beta 1 plus this times some beta 2. That's called a subspace in mathematical jargon, which I have to tell you that I love. So here's a comparison of the regressors. The AM1 is on top, and the two AM2 regressors are on the bottom. Now, suppose that we have a time series of data that looks like the bottom, the AM2 regressor number 1. That is with noise, of course, but it doesn't care about the ABI parameters. It's just some low-level function area or something like that. So then, what do we get if we did it with regression like this? we did it with these two regressors, we get a big beta for this and a tiny beta for this, which would all come from the noise fluctuations. And so that we'd say, well, that's a tiny beta with a tiny t statistic. Fine, this one active, but it's not differentially active. But suppose we regress with the AM1 regressor only. Well, the correlation coefficient between the AM2 constant regressor and the AM1 regressor is not zero. Those things are very highly correlated. Where one is up, the other one is up. The correlation coefficient is something like 0.6. So we would get a positive beta if the data looks like this. We'd get a positive beta, and then you might say, look, I found something that depends on the ABI parameter. Yay me! Except that would be nonsense. So AM1 regression is not useful for looking for amplitude modulation. The first actual user of this, which was really quite one of those synchronicity things, I wrote this just thinking it would be interesting maybe someday, and then about a week later, a postdoc named Whitney Postman walked into my office and said, I need to do something, 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 and it turned out that this was essentially what I had just done, sort of on speculation. Her task was picture naming in aphasic stroke patients, and I really don't understand the neuroscience, but it was good enough to make nice pictures that went on the cover of some stroke journal. It was got her a job as an assistant professor, so I think it was successful. Although when I look at these brain images, I feel sorry for the poor subjects. So you have an alternative. You can use IM regression to get the individual betas for each block and event, and then do something else to those, another regression, for example. You could do nonlinear fitting using the 3D NLFIM program, which I'll mention at the end of this talk, or you could do basically the sky's the limit. Your imagination is the limit. What's better, AM or IM plus something else? Well, if you want the linear fit of the amplitude of the ABI, then you really should use AM. We have done it both ways, and it's just better to go straight from the data to what you want rather than putting in two regression steps when one can do it. But if the AM doesn't fit your ideas, what you want to do, then you have to use IM plus. And if you don't have any local help, you might have to shoot us a message to get hints and advice. Recommend our message board. And there's another AM regression, DM regression, which is duration modulated regression. Exciting. And here's a cartoon of a real experiment, a visually presented puzzle. The subject sees a puzzle projected on the screen. The subject thinks for a while about the puzzle and then responds with the solution. And the timing when is measured, so you know when they press the solution. And this is from a real experiment, a sample puzzle. Here are these two block figures in 3D. Are they rotated from each other, or are they different 3D block figures that are trying to trick you? That's not an easy problem, actually, and the farther apart they're rotated, the more difficult it is to do. So if they're essentially parallel, people can do this almost instantly. But if they're rotated a long ways apart, it may take 9 or 10 seconds for a person to give a reliable answer. That's a lot of difference. This variable duration of the middle phase, which is probably the phase that you as the researcher care about, what's the puzzle solving part of the brain in this case, means the shape for the task will vary between trials. As long as the variability of duration is more than plus or minus a TR, then this is kind of contrary to the whole idea of averaging trials together to get decent statistics, saying it's the same shape every time, then we have a problem, right? So that leads to duration modulated regression, where different stimuli in the same stimulus class have different and known durations. Unknown durations is a whole separate thing. And this is done in AFNI by specifying not block, but DM block, which is the same thing as block, but the duration is provided in the stimulus file, married to the stimulus time. So it's the same as before. You have start time star parameter, but the parameter is the duration. Remember, the times in AFNI are always in seconds, not TRs. You can use Stim times AM2 and add an extra amplitude modulation parameter if you want. In that case, remember that the last parameter is always the duration parameter, and so if you had time, amplitude parameter, and then duration parameter, you'd have 2 stars in there. Try again not to go crazy with parameters, because that way lies statistical madness. And this is just a cartoon figure, which is just showing you that the program actually does what it's supposed to do. We have this toy file q.1d where we have 10, 40, 70 as the start times, and 1, 2, 3, 4 durations, and we see it gets wider and wider as it gets as the time duration gets longer, which is what, of course, it's intended to do. And you can get this script, which isn't really very lengthy, of course, from the AFNI website. There are a couple of other linear regression programs in AFNI, which I'll mention for completeness. There's a program called 3D Fitter. This solves linear regression models that you construct yourself. You construct the columns, the regression columns yourself somehow. It doesn't have any block model or something like that built in. One of the things it allows, though, is voxel-dependent regressors, and it has different solution methods, not just least squares, but it has a method called lasso least squares, L2 lasso, and it also has for least sum, instead of least sum of squares, least sum of absolute values solution methods. And you could put constraints on the fit parameter sign, so you can say this beta must be a positive number, and this beta here must be a negative number, and these other betas, I don't care. So this thing doesn't do any statistics, it just calculates fits. And then there's the program 3D Project. This doesn't calculate fits even, it just calculates the residuals. There are no statistics, no betas. This is used when there are only nuisance regressors, and the idea is to clean up, or as people sometimes say, regress out these nuisances. The most common nuisance, of course, being things from the subject head motion. And polynomials, or whatever you use for baseline modeling. And the use cases for this are primarily resting state fMRI and naturalistic fMRI, where you want to clean up the data before you go on to further correlation-based analyses. So you don't want to correlate motion artifacts, because they'll be correlated and they don't have a lot to do with brain activity. The reason is you could do this with 3D Deconvolve, 3D Fitter, 3D RemelFit. The thing is that those programs, because they do a lot of other calculations, are slower. This program was designed to be fast. That's all it's good for. And the final slide in this progression is nonlinear regression. You can try to fit a hemodynamic response shape of the form h of t is equal to a times t to the power b times the e to the minus t over some constant c, where a, b, and c are unknown parameters to be estimated. A appears what's called linearly because it's additive or directly multiplicative. That is, if I double a, h of t doubles in size everywhere. But if I double b, it doesn't change just change things by a scaling factor. It changes the whole shape of everything. If I change c, it changes the whole shape of everything. So this is not linear, which there's a whole vast technology of linear analysis that's been developed since the 1950s in the advent of computers, and to an astonishing extent, our modern society depends on linear analysis, linear regression, and other linear algebra stuff. Nonlinear is much more difficult to do because all it means is not linear, and that doesn't give you a lot of guidance on what to do. But we have a program for that. The caveat is that you have to provide a C function that computes the model time series given a set of parameters. We have 3 parameters here, A, B, and C. Input those, calculate a model function, and then compare it to the time series data. And we can help you with that. There are a lot of sample functions in AFNI source code distribution. And then 3D ML basically twiddles the A, B, and C parameters around until it finds the best fit in each to make the model function be the least squares best fit to the time series in every voxel. This has been used to create brain maps of pharmacological models for dynamic susceptibility contrast MRI or other IV supplied drugs. For example, there have even been studies with injected cocaine. These are difficult experiments to carry out and difficult experiments to analyze. So if you want to do this, be prepared for consulting with us and be prepared for some extra work. So thank you and stay tuned for more.